My name is Michael D. Campbell. I am chairman of the Uranium Committee of the Energy Minerals Division, and we have put together this presentation concerning the sources of rare earth elements in the United States and in the world. I'm joined today in putting together this presentation, Bob Gregory, who is Vice Chair of Government for the UCOM Uranium Committee. He's from the Wyoming State Geological Survey. I'm also joined by Stephen Sabray, who is, serves as Vice Chair of Academia. He's from the University of Nebraska. Also, James Conca, who is a well-known energy expert in the world. He also provides a lot of input over the years, and he's a member of our advisory group. Now, let me explain, since we have limited amount of time, this presentation was put together for long-term use, in that we have added a lot of references, links to papers that we'll be discussing, only summary. So let me lay the foundation in that way. We also bring your attention that members of the Uranium Committee also presented another paper by Stephen Sabray in theme 9, and we suggest that you may want to look at that as well. We've provided a link there on this this presentation, should you want to download it and convert it to a PDF. At this stage, let me explain that we're going to be going rather quickly, and we may run out of space and time. Let me briefly tell you about what we're going to be covering during this 20-minute or so presentation. Of course, we're going to be talking about the sources of rare earths, starting with their distribution in the very beginning in the universe, and then in the solar systems, and then on the moon, and meteorites, and earth crust, seafloors, coal and lignite, and in the groundwater, oddly enough. We'll discuss that in a little detail. We'll also be talking, of course, about the mineralization and the processes of rare earth formation, and how they're often associated with uranium and thorium, which is primarily the reason we've included it in the Uranium Committee as a subject of discussion and monitoring. We'll discuss also some of the deposits in China and in the U.S., especially in Texas, Wyoming, New Mexico, Colorado, Idaho, and Alaska, although there are a few others elsewhere. But we'll also be discussing those deposits and mines in Australia, and projects in Greenland and Scandinavia and Russia. Of course, there are others in the world, but those are the principal ones we chose to discuss during this presentation. History and development of our rare earths started a long time ago, as chemists and other industrial people began to recognize the special properties of the rare earth group of elements, and their use is expanding rapidly. As new applications were developed by the academic industrial complex, I like to call it, that stimulated major research, and by 2010, there was a huge amount of industrial development, and the prices of certain of the rare earths reflected that we'll be discussing in a few minutes. Rare earth demand through mining and prices have increased, but as China started holding back from some price-controlled rare earths, that created a rare earth price boom of the period of 2010 to 2013 that we'll be discussing in a little bit. Other rare earth sources are being sought, but as co-products from metalliferous mining, recycling of electronic waste, and as I indicated earlier, even from coal, waste coal ash, and byproducts of phosphate mining, and other sources that are beginning to get involved in the supply chain. But again, it depends on the price and the cost to produce. The competition in rare earth mining and processing, quite frankly, as a bottom line here, depends on ore grade and specific rare earth availability with the rare earth demand expanding. Right now, last year, 2018, the world only produced about 170,000 metric tons of rare earth oxides. And in 2019, that number went up to 210,000. So you see, the market is not large, but it's expected to expand to 7 to 10% per year. That's compounded, and so it won't be long till we'll be up into the 500,000 tons a year, and depends on, of course, the market. And that right now depends on the pandemic notwithstanding, let's say. Where did the rare earths come from? Well, they came from the universe. They came from stars primarily. And I must say, in our research, we ran across a very interesting presentation by Johnson et al. And others in a 2020 paper that presented this particular table of contents, showing exactly how stars came into play here. You'll notice that the rare earths, the lanthanide series down here in the bottom, are stuck in there, but below that is the actinide series, which makes you think about maybe this whole table of elements is not quite right. If you remember the movie Contact with Ellie, she got finally help into how to put together the plan. So I get the feeling, and we've discussed this, that we don't quite have the table of contents together right, but hopefully one day we will find out. But let me get to the elements here. The rare earths are spread all over the universe, and they're known and are present and are distributed in dying low mass stars and by merging neutron stars. The cosmic or the solar system fingerprints widespread rare earth dust, therefore, and once it arrives on Earth, you'll see in a little bit how it's distributed in a similar way with the help of volcanism. The lanthanum and through neodymium were formed by the low mass stars, then by merging neutron stars, as Johnson and her associates have figured out and have laid this whole table of contents of periodic elements out for you to see in a rather interesting way where all the elements, but particularly the rare earths, have come from. A particular interest, I got to say, is promethium, which occurs in between the samarium and the neodymium and the samarium. They're formed by neutron stars, then more by low mass stars. But promethium, as we'll discuss here in a minute, is quite interesting. I would say that about 14 of them are shown here that are in use, but we also get into the critical element area where scandium and yttrium, although it's considered a rare earth, but also gadolinium, and there's a few others. We just finished a major report on indium, by the way, and so all these other elements that have never been used much are finding uses that is quite interesting. Promethium's story is fascinating. I would encourage you, if you're at all interested in the origin of these kind of things, we put a link here for it and take you to a paper that is good. But it turns out that it really doesn't occur on Earth. It's such a small amount, they could barely find it. And because all of its isotopes are radioactive and they decay out. But the decay also comes from neodymium and other elements that you can read about. And so they're starting to find how to build up the reservoir of that from a few ounces to a few pounds and all that. And it turns out that promethium is extremely useful in batteries, in nuclear batteries that we're going to be using off-world in some of our space work and asteroid and lunar activities, which I find that interesting. But anyway, starting with the rare earths in the beginning, the Odum-Harkins rule. It turns out that the distribution of the rare earths are guided by the nuclear synthesis of the original formation, and those are inherited throughout the distribution. Oddly enough, they hang together, and we have included some plots here pretty soon. It basically starts with the relation between hydrogen and helium and the nucleosynthesis that occurs, that's reflected in the bottom right of this particular slide. You can see it always goes to even, and the distribution and concentrations are therefore are reflected unless there's an outside influence, which we'll demonstrate in a little bit. I'm also including here the updated periodic table on the bottom right link, but here's another periodic table that Raosbach put together some years ago that's particularly useful to geoscientists as we deal with various elements in our field. Okay, let's look at some of the distribution of the rare earths, starting with in the lunar samples that we recovered from the moon over the years, and from meteorites. You notice the sawtooth pattern from the nuclear synthesis of hydrogen to helium, or helium to hydrogen, etc. And you'll notice that the moon, some of the moon's sample up here, 190 ppm, are getting into the significant range in terms of economics. Of course, this is in the light rare earths, and might as well explain that now. The terminology is used for a difference distinction between rare earth groups, and it's the light ones. The light group, it runs from lanthanum through cerium, praseodymium, neodymium, samarium to europium. You notice in between neodymium and samarium, there's an odd extra. There's no dip in between here. This is where promethium, that's a bug, isn't it? Promethium belongs, but since it's practically non-existent, until recently, it isn't usually included in rare earth plots of any kind, whether they're put into ratio with meteorite, chondrites, what have you. You can still see the typical sawtooth pattern. What we're looking at is the changes of the relationships as you get from the light rare earths up in this part of the rare earths down into the heavies, which starts at europium and goes through gadolinium and terbium and dysprosium and holmium and down through the lithium. How these start to flatten out in concentrations are sometimes reflected and sometimes they're not. I guess the important thing here is in lunar projects, there's no doubt that we're going to be able to get up there and spend some time, and we'll be looking for rare earth anomalies in the sampling, in addition to the helium-3 that actually was discussed by an earlier Energy Minerals Division Memoir 101 on activities off-world that I would recommend you have a look. It's in the link here on the right-hand side on this particular slide. Let's take a look at the next. I've listed down here, or we've listed down here, all the meteorite samples that we could find, in addition to some of the Apollo samples and what have you. Okay, let's go on to the next slide. Okay, here we're looking at the rare earths in the upper, middle, and lower continental crust. There was a major effort over the years to try to get some idea of what the rare earths occur, or how the rare earths occur, and in what quantities do they occur in the crust. And there have been a lot of studies done. We picked out those that have appeared to prevail in terms of the general discussions that go on. And you notice again, it shows the sawtooth pattern. But here is one of the anomalies that we picked up on the crust, that you notice down here where there's a floor. We're calling this a floor because instead of just keeping on going down in concentration, you see and these are averages of a lot of samples, by the way. So these averages are meaningful. It doesn't give you an error bar here, but these are still meaningful, and it suggests that there's some sort of a perhaps fingerprint on all three of the continental crust investigations that have happened. And same with the last two rare earths are down here on the bottom, are shown almost identical. Looking now at the Atlantic and the Pacific Ocean floors, you'll see the work done by Balaram. That's showing a similar kind of floor here. Now, mind you, these are samples from the seafloor around the seamounts, and these samples are hanging together, and these again are averages, so they're meaningful in a general way. But you notice there's a floor here and another floor here. And these concentrations on the seafloor can be quite high, and therefore industry is crawling all over it. I mean, looking at it in great detail. Of course, it's not only in the Pacific and the Atlantic, but also in the Indian Ocean. There is some environmental concerns because the bottom disturbance tends to, let's say, interfere with well, let's call them critters. And that is something that actually my son, who is also a professional geologist, he runs he has considerable interest in the oceans. He is founder of the marinebio.org, and he doesn't think that we should be doing much on the seafloor. And he and I have interesting conversations from now and then. Now, turning to rare earths and coal, since China has done so much work, it's one of the things we notice in the industrial complex explosion in 2010. The Chinese have spent a lot of money and effort on looking at Chinese coals, and we put a link up there for you to look at, and you can see that it reflects a similar sawtooth, but you notice there's no floor. It goes all the way down in sawtooth without bottoming too much. If you look at the average of all this, you'll see that it's not much of a floor there, although there's a little floor here. To such an extent that even this stimulated, no doubt, the U.S. Academic, government, and industry activities into funding coal research in not only coal but also in lignite. And you'll see here all the groups that have been awarded contracts to look at them, and we've included a history here in this link that covers a lot of those studies. And I must say, when you go to this history, you'll see you're being taken to the I2M web portal, which I could go on at great length, but we don't have time. But it's a collection of almost going on 10,000 papers or reports and what have you that we put together over the last 10 years. And we add to from people like you out there that send us interesting reports that we haven't already found. And there's a searchable database, and we can arrange them by time or by date and by subject. So I would refer you to, if you want to look at that, and any other subject in geoscience that's of interest to myself and my son and others, associates in I2M Consulting Group, that you might find interesting. Okay, now we get to the really interesting parts, only because I've been working on this for some time. We ran across samples in a project. I won't go into any detail, but the whole it was a major groundwater sampling program, and we kept finding sort of unusual amounts of rare earths in shallow groundwater. And so we did some detail for other purposes, and would be able to get into the very small particles, trying to figure out where the rare earth resides in the particles that are reporting as solutions. But obviously, when you digest it with acid, a sample with acid, you remove also all the colloid size. But we wanted to see what the particles were. And so you'll see these two plots here are based on 0.45 filters, solid line, and 0.10 filters on dash line. And you notice the seesaw pattern is still reflected, except that you see a major, what we're calling a europium floor, only because it starts at europium and remains rather similar, but also rather flat. That's being reflected as interesting colloidal, otherwise nanoparticles, even are showing a rare earth fingerprint. This we figure reflects dusting from a anthropogenic source, or from past volcanism, or from small meteorites. Here's a distribution of the rare earths in the groundwater. The whole line goes from lanthanum over here to lithium. And you'll notice that these are different monitoring wells locations here, and you'll see the higher levels of the lanthanum and the rare earths on these are also matched with the higher levels of arsenic presence. So I can't go much further than that, but it's still remarkable how this tends to show up. Let's get into the really interesting things worldwide and in the U.S. As you probably have heard, there's a place called Mountain Pass that is a major carbonatite, and that definition is included here for you if you want to click on some of the references. And I won't have time to go into too much detail, but Mountain Pass used to be our major producer of rare earths for many years, until the economics and the environmental issues got a little troublesome, and they had to slow down. And about that time is when China got into the mix and started controlling all the distribution, or most of the distribution. But let's look at this map first. Here's China, and I got to say, China's got huge amounts of high quality, high grade rare earths, and not just one, not in the inner Mongolia right here, but they have other major deposits, and some of them are carbonatites, and others are alkaline igneous related to intrusions. So you can see here they are here, but here's Mountain Pass. But at the same time, here's the New Texas project. Here's the Eastern Seward Peninsula project that we've been working on. You'll see the Kola carbonatite here is discussed right over on this side with a good link that'll give you an idea of what's going on. This is not developed yet, but as you'll see in a later slide, Russia has a fair amount of rare earths as well, and we'll see how that goes. And as you can also see, various deposits, both carbonatite and peralkaline igneous intrusive types of occurrences are not uncommon in the world and increasing rather rapidly as exploration expands. Excuse me, but the heavy minerals are also have plenty of monazite and other rare earth containing sands. And there's a few deposits that are residual clays that have retained the rare earth and it didn't wash away, let's say. And of course, the phosphates in the world, not only in Morocco, but in Queensland and Northern Territory, where I worked on in the early 60s, that I noticed that had a fair amount of rare earths in it. And because these are bulk mines, that means huge tonnage, there's a huge amount of secondary available rare earths in these kind of deposits. Okay, let's move on to the next slide. Here's a distribution more recently, 2019, of some of the deposits. I won't spend much time except this. This is a small print here, and I'm expecting that you're looking at this on the computer monitor and not, like at a big theater. So you'll be able to read this small stuff, and that's the reason we've added small font and not used all big letters that would jump out at you. So anyway, this is for your secondary consideration. Items of interest right now, we count up about 55 known rare earth occurrences, and the numbers are increasing, as I said. And those are coming in Canada, and more in Australia, and of course I'll bet China is still looking other areas, mostly looking for shallower, less expensive to mine kind of projects. There are so many, in fact, that as I say here in the bottom right, and to remind me to share with you that there are so many of these particular deposits that many of them will just end up as sites for geologists' field trips in the future decades ahead. So, oh yes, we have plenty of rare earths, and that's what we're getting to here. And here's an example, especially like in Texas. Some of the modeling we've included as to the different types of rare earth emplacement. I won't go into any detail. You can read this and study this. In fact, our whole presentation is presented to you for secondary follow-up for detailed evaluation. That's the reason we've added the links and the various graphics here. I want to emphasize that this is probably the most common type of intrusive rare earths that contain very large amounts, high amounts of rare earths, usually in fluorine veins with high amounts of uranium and thorium. The project in the eastern Seward Peninsula that we're working on, the paper which we produced a couple years ago, will give you some more details of this. The rest of the types that are dealing with cyanide or carbonatite occur in New Mexico and related, and there's a reference there for you to look at that. We've also provided all the references for each one of these figures so you can follow up in some detail. I want to emphasize also about the seafloor here. This shows on the right is a outstanding graphic for that you can click on, and it'll expand. That shows you just how a lot of the rare earths have gotten into the coal and lignites in the world, which is understandable from volcanism and perhaps meteor breakup. The mother lode, if you will, of rare earths right now. This is the Banyan Obo rare earth mine complex. There's more than one mine here. You can see a pit here, and a pit here. These are all waste piles, tailings piles. Those are the ones that mostly get the down in here, and here's some more waste piles. Those are the ones that usually get most of the PR. For example, in 60 Minutes, if you happen to see that one that piece that they had a few months ago, that was, they emphasized oh, look at the waste piles, and isn't that terrible? And yes, there's environmental issues, but the Chinese get after these things, and you can see there's a town built right on top of the mine to provide the help and assistance. And I understand that the Chinese are beginning to add new environmental controls and improve conditions. So they know what they need to do, and it's just a matter of the oil with the world, with their eyes on, well, with the world's eye on what's going on, they'll respond. So these mined ores and processed oxides are being developed, but China is also realizing that not only do they need to just produce the rare earth, but they also have to, if they want to keep control of much of the market, keep control of the produced metals and the alloys that are being used, and the end products such as magnets that goes into electric cars and rail lines. And at the other end, they have figured out that not only do they mine, but they also have to sort of control other sources. So we know for a fact that they're out talking to a number of people, mining companies in Australia, for example, and South Africa and elsewhere for acquisition of those projects. And of course, they would put them, they wouldn't develop them, or they would develop them very slowly to protect their production, not unlike De Beers does in the diamond business. So this is nothing new. This is just pure capitalism, and we have to compete accordingly. This too is a table of small print, but it's for your benefit. It shows some of the older rare earth deposits been known for years, so it's not like it's new. Finding rare earths are new. We've known about rare earths for a long time. It's just we found out that some of those rare earths have some really interesting applications, and so all of a sudden the demand is starting to go up. Here's some of the Mountain Pass descriptions in some detail. Excuse me. And Castor in 2007 described all the older products, all the older rare earth sites in some detail, if you want to take a look at that. The one in Texas that will likely be on in production pretty soon, because not only do you have to mine it, if you really want to get into the rare earth business, you also have to process it into oxides before it has any major price to it. And that's what the USA Rare Earth Company, which has sort of taken a lead in the projects in Texas. The Texas Mineral Resource Corp did the development, early development, although this deposit was also known for some time, but they didn't know how useful it might be. And by useful, I mean it not only has rare earths, and you can see here's some of the sawtooth, but if you notice, it's heavily enriched, excuse me, heavily enriched in heavy rare earths, which is some of these products are extremely high priced. So, but it's not only that. It's also because the deposit has hafnium and beryllium and gallium and zircon and what appears to be economic concentrations. But at the same time, there's a sulfate byproduct that is being considered to come out of this thing, and that's going to be producing sodium, potassium, manganese, magnesium, iron, and even some aluminum. Excuse me. The other thing about this Round Top deposit is that it's near rail facilities, just a few miles away. I remember I passed it, the site on I-10 going west many times, and there's a rail line, east-west rail line that comes across over there that they'll be able to provide. It provides market access to them for their bulk product distribution. The mineralization there around top is, excuse me, is in rhyolite as opposed to igneous and metamorphic intrusive igneous, not intrusive igneous. This is intrusive, but it's a rhyolite, very different kind of thing, and some odd minerals. But the bastnäsite here is your common rare earth containing mineral that is mostly produced in the California deposit as well. But there's other elements that contain, and each one of these minerals have to be, let's say, broken up, and the rares have to be released in a special way. That's why Round Top is coming on rather strongly, because they've made a deal to develop a reprocessing plant and refining plant in Denver that's underway right now. And if they can get that underway and get their products ready, they could be in operation in the next year or so. Most of the other projects are looking at lead times of 5, 6, 7, 8 years out, which, there may be some merit to that. But this is a particularly interesting because it's a heap leach project. In other words, they mine it and then put it in a big pile, and with various fluids they can remove a lot of the rare earths, and also some yttrium and scandium comes out, come to think of it, of this heap leach project. So we'll talk a little bit about a basket product, meaning rare earths has this unusual capability of having many products, and each one has different prices associated. Sometimes you can get a very large amount of money for one element and not so much on another element. When you put them all together, makes exploration and development interesting. On whole, Texas is under development for these particular kinds of projects, so I expect more is going to be showing up. Of course, they have to end up with special relations in terms of what's present and what's marketable. So Bob Gregory up there has told me a lot about what's going on up there, and he's involved in the production of both large scale reports by the Wyoming State Geological Survey, and he's telling me about the Bear Lodge deposit that has also been known for quite a while, but with the prices going up, they're starting to take a closer look. So here's some of the details of it, and here's a good reference to both of his reports are right. He and his associates there at the Wyoming State Geological Survey. So you also get the feeling that Wyoming is also not so well explored, because you see on this graphic on the left-hand side, there's lots of samples that are showing let's call them anomalous rares, usually lanthanum as a guide, only because it occurs, and cerium mostly occurs as the highest concentration. But anyway, again, throughout Wyoming, there's association with uranium and thorium and some of these prospects, but there's rares everywhere to look at. Of course, whether they're economics, it's another matter. A similar thing over the years, they have done a pretty good job of finding out where the old prospectors have dug around and come up with, let's call them rare earth shows, but they've been looking at more detail recently. There's an interesting article here by Anderson, an article in 2015 that found some anomalous rare earth associations at the KT boundary. The next is in Colorado. The U.S. Geological Survey has known for some time about this Iron Hill carbonate carbonatite complex near the town of Powderhorn, and it's being looked at. There's one of the original papers by Van Goosen to USGS. And there's some other issues here around Iron Hill. You can see on the left down here. These X's are other kinds of metal mines or products. This whole area is heavily mineralized, so Colorado has a lot of potential also. And again, depending on whether they can find good reserves and grades. In Idaho, Lemhi Pass is well known for years. They're taking a look at that, and you can see back in this late 70s, some Stats and others took a look, and then more recently, some of the Diamond Creek vein deposits were looked at in some detail. They weren't looking necessarily for rare earths, but they were looking for radioactive areas. And then once they found the radioactive minerals, they found out that those minerals also contained significant rare earth elements. In Nebraska, the Elk Creek carbonatite was discovered in 1970, and that's been looked at academically for some time. And you can see it's about 630 feet deep to the top anyway. It's iron-rich bearing carbonate rock. Someone has decided that has to be a carbonatite. And Molycorp, the original owner, the primary owner of the Mountain Pass deposit in California, has also looked at this over the years in detail and have decided that it's at least a prospect. Cameco, another major mining company, and NeoCorp has found the Rio, the rare earth distribution almost up to 2%, which is interesting in terms of grade, and more interesting also is the way in oxide here is running a 0.5%, which is another one of those market basket things. If you have more than one product, it may make the project economic. And there's a couple of references there, and other work done. Paragenesis was looked at as early as, or as recently as just 2017, and that's interesting paper. In Alaska, as you might imagine, or maybe not, but as everyone went to Alaska for gold mining in the 1800s, there's also showing that there's other minerals as well, not the least of which are rare earths. And in this case, in the Bokan Mountain area down here in the bottom, which is barely Alaska, admit, but it's still ours. It is a major rare earth uranium and thorium occurrence, and it's got some mineral resource estimates of up in the millions of tons, and grades that are pretty healthy, about 0.5% of total. That's the whole market basket of rare earth oxides in terms of rare earth oxides. One of the other areas is Cochuic Mountain areas in the far western part of Alaska, on the eastern part of the Seward Peninsula, which this is where we worked at Orion in the late 1970s and early 1980s, and it's a igneous complex that shown up with dikes like that guide I showed earlier, has shown very high rare earths and thorium and very high uranium. This is a sample here of the alunite minerals, which contains some, if not most, of the rare earths. There's a black crystal. They look like cumulates when you're in the field, and then when you do thin sections, you can see them here. You notice these things are all heavily fractured, like there's been some major movement after these things were in place. Then when we started looking at the overall area, we noticed that this area is right next to a very large, round, well, circular basin that we got to thinking, you don't suppose that's an impact crater, do you? And so we put that on the list the next time we're up there to go drill some shallow holes to get some samples of the interface between the underlying bedrock of the basin and the tertiary sediments in that basin. That should tell us, everything we need to know in terms of micro silica pieces, iridium, what have you, as to whether or not this was an impact crater. But that was a large one, 30 miles in diameter. That must have taken out a few trees. But anyway, I won't go into any details because it's the references down here listed in the paper that we put together based on the 1970 and early 80s and subsequent work on that area. This is, we included this because this is from the survey, U.S. Geological Survey of rare earths. And this shows you how much rare earth there is in the world. You notice this is all the way from lanthanum down into the lithium. And you notice that they're just everywhere in the soils in and around this particular area. Now, whether or not this is because there was a major distribution of rare earths from perhaps meteor impact or erosional issues of spreading out this material, but it hangs together. This is the area of the mineralized zone that we discovered when we were there and have done some work on. You can see some of the mineral constituents. For example, this cesium or cerium here is more than 10,000 ppm. And that's, if you could put it into oxides, that's major grade. So I won't spend any time on this any further. You can take a look at it in the paper. The country that has the most to offer from rare earths, not only because there's a lot of rare earth deposits, but primarily because Australia government, state and federal government, are extremely supportive of mining. I spent 4 or 5 years down there working for Conoco Mining Group, and I was absolutely amazed by how much the government supports the mining industry. And yes, they have environmental controls, but the mining people there in the hundreds of mining companies, they all know that, and they do exactly what they need to do. And sometimes, of course, there's a mistake made, but the government has exercised the appropriate regulations and took care of things. So I'm just going to give you a few of the ones that are well known. Mount Weld here is a major producer right now. Mary Kathleen mine is very interesting. I was in that mine. It's an open pit mine, and it's like a different world. It's incredibly dark. The whole pit is dark orange to black to brown, and you get down in it and you don't think you're even on Earth. And the area is just so heavily mineralized with all sorts of odd rare earth minerals and what have you. That is essentially mined out right now. And of course, Milo here is an extension. They started drilling next to it up a trend or what have you, and found some more. But Olympic Dam is an ongoing project. This is another instance of how you have a market basket of more than one project, more than one product. Olympic Dam is primarily a uranium mine, but it also has a fair amount of rare earths in it. But they're not now. They're stockpiling that for later treatment and use. But it's still a major source of rare earth because it's a huge project. It has been. Olympic Dam has been going on for decades. Okay, Greenland, down to southern part of Greenland, all sorts of activities going on with respect to rare earth. This particular one, and I never have been able to figure out how to pronounce, but I recognize it. Ilsmakrup complex. It's got major rare earth and uranium and thorium, and this will probably be developed here pretty soon. It's also a project that the Chinese have been discussing, wanting to be a partner, a development partner in. We'll see where that goes. Now, over here in the history of this Greenland activity, I've included here under there's more. This is a good. This takes you to the I2M web portal that describes the a number of papers that deal with the development of the Greenland rare earth deposits. Okay, over in Norway, Norway's got some shows. None of them yet are being produced. This Finn, this particular project, Finn is under, let's call it development, and the one next door is under some development. Whether they actually produce or not is I'm not aware of right now. But what I want to emphasize is, you see this right here? This is Finland, right in here, and here's Russia. Here's the border. See the border of Russia and Finland? You notice some of these very interesting and important deposits of this particular one, Lavara and the Sukli. Those are major rare earth deposits, and it's right on the border. And I don't know about you, but I would be a little nervous about working on either of these, although Russia has apparently plenty to keep them busy. Here are some of the references that you might find of interest, especially the Russian one here by Ratsiev, done in 2014. The summary of development. Uranium have been mined since 1900s, and as you can see, in about 1960, 1950, we started finding uses. You can see in 1952 is when Mountain Pass in California started mining, and then you can see this is certainly not linear, but this curve on world production and demand is going up rather quickly, and with all the changes in the demand depending on the world and local financial conditions. The technology has been driven by geoscience research. It's been driven by geoscience discovery and more research, and then comes the industrial applications, engineering applications. That's clear. This is a geologically driven process of exploration, and which is true for all natural resources. Industrial development, of course, depends on the exploration, but also on the grade tonnage evaluations to how far it gets along, whether product demand or resource price or economic pressure, or even geopolitical interaction comes into play. That means with all this activity, there's a fair amount of jobs at stake here, and we've included lists for jobs links in Australia, the UK, and the US here for your particular benefit in case you should need something like that. This is an example of the boom that was going on in 2010, 2011. This shows the price for Chinese money for dysprosium, which is clear up into equivalent of about $2,800 for 20,000 kilograms, or you can see it translated here. So as you see, this came down as more discoveries came to bear, and this is when China put the brakes on and then slowly started releasing products into the market. You saw the price of dysprosium actually go down. It's going back up now, but this is for all sorts of reasons, primarily because other sources are beginning to become available. You can see that the cerium is not rare. It has 60 ppm average in the crust. whereas the other rare earths are at less than 1%. The rare earths are also associated with uranium, as I've said before, and even that, and many of the rare earths are more abundant than gold and silver. So the world reserves of rare earths are increasing with exploration, just like when uranium is under exploration, the reserves increase that way too also. But as with most natural resources, including oil and gas, the market dynamics and research investment in alternatives will ultimately determine the criticality of the elements. You can see there's some nice graphs, plots here of what's desirable, what isn't. Dysprosium here, dysprosium here is, as you can see, very highly sought after for magnets. We've gone from 170,000 tons to 210,000 tons. It didn't take much mining to make this kind of production. So this is fairly small, but critical. China has control of 71 and increasing up to the high 90s recently. But they're having trouble with illegal mining because they can't seem to control it that much. It's probably leaking out of border areas such as Vietnam and elsewhere. Here's a discussion of when the Mountain Pass was increased to in 2019. They're back online now, and they just produced 26,000 tons. So they're beginning to contribute again. And that, I think, will increase, but we'll see what happens on the economics. Australia has a number of projects that are, as I said, that are coming to fore, and they're second in the world in terms of producing right now. That may change as other countries get into it. Russia has a number of deposits. There's a couple in the western part or eastern part of Russia that is rather large too. We haven't discussed that. Some of the distributions of where the grade tonnage, grade versus tonnage comes in, and you'll see here some of the ones we've mentioned already are put into perspective, and same over here. Here's the large Chinese, and here's Mountain Pass, here's Mount Weld. I think over here's Round Top. You see, it's not the highest, not the lowest, but it's up in there with the other deposits. Lanthanum in 2019 was going for 168, $100.68 a kilogram. Yeah, $1.68 a kilogram. And in 2020, it was up to $330, $3.30. Sorry. And so that's a big increase. But at the same time, you look at praseodymium, and it was up to $54. But in 2020 it was down to 41. Other ones like terbium, that's going for $575 a kilogram. That was terbium. That went up to $650. And so you see evaluating the economics of these mines tend to be a little dicey because you can't put your finger on the right price. That you don't want to be too high or too low. We do that. We have that problem all the time when we're evaluating mines, especially the ones we've done in Australia, because it's market driven and how you do the this is a busy slide, but you're going to be sitting next to your screen, hopefully, and you can take full advantage of this. I put all the deposits in perspective here, and even in Namibia, a major rare earth, but it primarily is producing yttrium, which sort of separates it from the others. Here you see it here on the top of the market basket, meaning it has yttrium, but also a lot of other things that you get good money for in the market. And here's the the main Chinese and deposit, and here's the round top. So anyway, I've summarized what the limitations of the rare earth basket price approach is, as opposed to just operation and maintenance costs, so and capital costs. So have a read of that, and I think you'll find it of interest if you want to know more details about the actual economics of and the whole overall scheme of things. You got the Chinese project, you got Mountain Pass out here in terms of its resource versus grade, and only the ones that have the higher grade are being produced that makes sense. And of course, with the Chinese out here top, they're dominating the market now because they've got really good resources, and plus government support. But in the future, up here to the Argus Research Group started looking at what are we going to need in the future of 2020, and you'll notice that the rare earths are hanging in there big time, and the volume, for example, let's say of magnets only producing of total rare earth 21%, but its value is 68% of the total value. So magnets are going to be huge. What about the trade routes? Well, it tends to be a bit of a mess, but you can see it's all coming out of China, and it will even the Mountain Pass products used to be sent back to China for refining. That if the Round Top project gets started, and especially the processing, then they won't send it to China. They'll send it to Denver so we develop our own rare earth processing. This needs some study, so I won't, and here's a reference for you down here in the bottom. But let me say that there's a price demand complexity to this, where you saw the neodymium dysprosium peak, that as mine products were developed, the price went down, but with increasing demand of 3 to 7% CAGR, which is the compound annual growth rate calculations, it's still going up. So we're in an interesting situation, and with respect to reserve base, there's a possibility that down here in the bottom you see that I mentioned something about the development of off-world resources. If in fact some of those asteroids are just loaded with rare earths, where we can get huge quantities of very high grade, all of a sudden all of the rare earth deposits on Earth may become uneconomic. Yes, it's going to cost a lot to get up there, but maybe the unit price of these rare earths will come down as we develop the technology. I'll close and suggest you have a look at the references and go from there. Thank you very much. I hope you have enjoyed what we presented here. And if you have any questions, be sure and feel free to call me at i2mconsulting.com. The number will be there somewhere, and we'd be glad to talk to you. Thank you very much.